Hey everyone and welcome. It's pretty wild when you think about it. How can your phone search for the idea behind what you're typing, not just the exact words? Well, today we're going to pull back the curtain on the magic that lets machines actually understand human language. So how in the world does it work?
It really all comes down to this one single question. Computers live in a world of ones and zeros, right? It's all just math to them. But our language, it's messy, it's full of nuance and context. So how do you possibly bridge that gap? It sounds almost impossible. But the solution? Well, it's nothing short of genius. And here's the big idea. We're going to bridge that language gap by translating our world of words into the computer's native tongue, numbers. See, we're not trying to teach the computer English. Instead, we're going to create a brand new mathematical language that represents English. So here's the absolute key. Instead of the computer seeing a word like ship as just S-H-I-P, it sees it as a long list of numbers, a vector. You can kind of think of it like a coordinate on a giant multidimensional map. And this vector, this list of numbers, doesn't just identify the word. It actually captures its essence, its vibe, its meaning. But where do these magical number lists even come from?
Well, we have to build a machine for it, a special kind of machine called a neural network. We're going to look at a model called Word2Vec. Now, don't worry if that sounds complicated. We're going to build this thing together, step by step, and you'll see it's way more straightforward than it sounds.
All right, let's look at the blueprint for our machine. First, you've got the input layer. Just picture this massive switchboard with one switch for every single word we know. We find the switch for our word and flip it on. That signal then shoots over to a much smaller layer. This is the embedding layer. If we want our final vector to have, say, 300 numbers, this layer has 300 little nodes. This is where the magic is going to happen. Then there's a hidden layer that helps the network find even deeper connections before it all ends up at the output layer, which, you'll notice, is the same size as the input, ready to make a guess.
Okay, so we've built the machine. Now, how do we teach it? It's like teaching a kid to read. You give it tons of material. We feed it a colossal amount of text. I'm talking all of Wikipedia, thousands of books, you name it. But just reading isn't enough. The network needs a specific goal to help it learn.
And you know what? That goal is surprisingly simple. The whole entire training process just boils down to this one simple game. You give the machine a word, and its only job is to try and predict what other words are likely to show up nearby. That's it. It's just a prediction game, played millions and millions of times. Now, these little training pairs, they have a name. They're called skipgrams. So if you have a sentence like, "The quick brown fox jumps," one skipgram might be, "Here's the word fox, now predict the word jumps." Or, "Here's fox, predict brown." We create billions of these little pairs. And by trying to guess the right nearby word over and over and over again, the network starts to learn which words like to hang out together.
So after all that training, after billions of these little predictions, something truly amazing starts to happen. This is the big payoff. This is the eureka moment, where our simple machine finally starts to get what meaning is all about. Remember that little embedding layer from our blueprint? Well, every connection going into it has a certain strength, or weight. And that weight has been getting tweaked a tiny bit with every single prediction the network makes. When all the training is finally done, the collection of all those final weights for any given word, that is its vector. We can now just look up any word and pull out its unique list of numbers. We did it. We've created our meaning map.
And the result is just brilliant. On this new map we've created, words that have similar meanings, like sail and ship, end up with vectors that are super close to each other. They literally live in the same neighborhood in this crazy high-dimensional space. But words that are totally unrelated, like ship and how, they're miles and miles apart. You see? The network learned about context, and in doing so, it accidentally learned meaning itself.
Now, I know this all might sound a little bit abstract, but I promise you, this one idea, it powers a massive amount of the AI technology that you'd use every single day. Let me show you what I mean.
Think about it. When you go to a search engine and type sailing and you get results about yachts or marinas, that's not just keyword matching. The search engine is using this meaning map to find related concepts. Or, when an online store suggests a new hoodie because you just looked at a t-shirt, it's because it knows they both live in the casual wear neighborhood on the map. This is the engine that drives everything from chatbots that actually get what you're asking to tools that can summarize a whole article for you.
And that really brings us to a bigger final thought. Because this isn't just about making better search engines. We've basically handed machines a key to understanding human communication, our knowledge, even our creativity. So the real question is, what other doors is that going to unlock?
And honestly, answering that question, what's next? That's what the entire future of AI products is about. If you're excited by turning these powerful ideas into things people can actually use, you have got to check out the AI Product Management Playbook by Deepak Dio. It's fantastic for staying on that cutting edge. Thanks so much for watching.